Okay, so let's move a step forward, at least to introduce the next subject, which is multi-objective calibration. Now I have a doubt. I am not sure if this part, which is short, it's very short. Multi-objective calibration is short, and it is useful because it allows me to introduce the next topic. So I don't remember if multi-objective calibration is covered by my documents on the website. The next topic, which I will introduce, yes. This one I'm not sure. Basically, I'm just saying this because if it's not available, I don't think it's a problem because it's very short. But just pay attention on, there is a video of this, but pay attention because I'm not sure. And in any case, if you have any, I have something to make available. So if you don't see it, please just drop me an email because I have a couple of slides that I can make available to you. Okay? I will try to make myself the check, but in any case, if for some reason you don't see anything, just drop me an email. So what is multi-objective calibration? Basically, is something that became much popular in recent times, in hydrology in general, and I think in system analysis in general, it became very popular in recent times. And it's the counterpart of the single objective calibration that we considered so far. Basically, so far I said, let's assume that we have to maximize an economical benefit. And this is a single objective. But you may have two objectives. For instance, economical benefit on one hand and benefit for the environment on the other hand. So you may have two contrasting objective functions, meaning that an objective function that gives to you the maximum if you use much water, another objective function that gives to you a maximum if you use less water. And this is often the case in water resources management. Very often you have contrasting needs. And even when you reach, when you talk with the stakeholders, they have contrasting needs. And let me make some examples. For instance, there is the person, the client that is interested in getting the economical benefit from water usage, that is interested in, of course, using more water as much as is possible. For instance, if the client is a person that is willing to pay for building an hydropower plant, and he is willing to pay because afterwards, by selling the power, he gets, of course, some money back. And he is willing to pay if the investment is convenient, and it's convenient if he has the opportunity to use a lot of water, to produce a lot of power. On the other hand, there might be the fishermen that don't want that the river flow is depleted much, because otherwise, of course, the environment suffers. And besides the fishermen, you may think that they, it's an opinion that is not much valuable. Let's think of other issues like tourism, downstream, if you have let's think of the management of a reservoir. If you manage a reservoir, the reservoir can produce a benefit for producing hydropower, but the benefit is also tourism. But if during summer you use a lot of water, then the water level in the reservoir decreases too much and the tourism doesn't work anymore. So you have contrasting needs. And it's not easy to reach. What you need to do is to reach a compromise, and it's not easy. So basically, one way of reaching a compromise is to devise an overall optimum solution which takes into account multiple objectives. And in any case, you need to define these objectives through objective functions. So in any case, or let's assume this, because otherwise you have to consider other solutions. But for the solution that I want to introduce, the multi-objective calibration, let me assume that you can quantify this objective in an objective function. So basically you have a situation in which, let's suppose that we have just two objectives, and the extension is straightforward. You have a situation in which you can depict the diagram, and in this diagram you can put objective 1 in the y-axis and objective 2 in the x-axis. And then, for each value, possible value of x, you find a point here. And what may happen if these objectives are contrasting? You find that to the highest value of MB1 corresponds a lower value of MB2 and vice versa. And in between, of course, these two solutions are not optimal solutions in a global sense. Because, you know, in this case, these two solutions, let's forget about the third one, these two solutions correspond to the maximum benefit for one of the objectives, but very often this is a lower benefit for another objective. These two solutions are extremely important. So the maximum for each of the two benefits, or whatever the number of benefits, this solution are very important for the definition of our problem. These are not the optimal solutions, but to identify the behavior of the problem, these are extremely important. Because it may be that you end up with a solution that is here, and then you are done. If you see that the two maximum are coincident, then it's fine. But usually this is not the case, because usually if you are called to solve a problem, it's because you find two different solutions for the maximum of the two benefits. Still, you may find that these are not very far, so you may find a situation where the two solutions are very close. And if it is like so, to reach a compromise is easier. Instead, you may find other situations more common where the two solutions are well distinguished, and then you have to find the best one. So, first of all, let me say that with such a problem, an optimal solution in the strict sense doesn't exist. There are compromise solutions, and then to identify the optimum, an agreement is necessary. But what is important in this case is to identify from all possible solutions those that deserve our attention. So let me make an example. If you have a solution here, this doesn't deserve our attention. Why? Because, you know, the benefit that you get from this solution is lower than the benefits that both the benefits that you get with the other two solutions that correspond to the maximum for one of the users, of the stakeholders. So why should I consider this one? It's better if I get this one then, because I have a higher benefit for MB1 and a higher benefit for NB2, so this one is for sure better. Or this one is for sure better. So this one sure is to be rejected. And the same reasoning can be done for many others, like for instance, other solution here that can be rejected. So, how can we identify these solutions that are interesting, that deserve our attention? And these are called non-dominated solutions. From an intuitive viewpoint, let me clarify what it means, that a solution is non-dominated or dominated. And let me consider, for instance, this solution here. Now, if you consider this solution and you compare it with this one, what can you see? You see that the benefit for the user 2, so let me call this solution S1, S2, and S3. So let me consider S3 and let me compare it with S1. So you see that the benefit of S1 with respect to S3, the benefit 2 is lower. So the benefit 2 is lower for S1 with respect to S3. The benefit 1 is higher. But we can't say that the solution S1 is better according to all the benefits. It's better according to just one of the benefits. So we can't say that S1 is definitely better than S3. Absolutely, we can't say that. Now, let me consider S4. And let me compare it with S3. S4 has a lower benefit for both the benefits with respect to S3. So S4 has a lower benefit 2 and a lower benefit 1 with respect to S3. So clearly the solution is not interesting. In technical terms, we say that it's dominated by S3. Instead, S3 is non-dominated by S1. S3 is non-dominated by S2. So, in poor words, I can say that a solution is dominated by another one if both benefits for that solution are lower with respect to the other one. This is in poor words. It's not a rigorous definition. But what happened here with S4? I found that both benefits are lower than the benefits of S3. So in poor words, if both benefits of one solution are lower than the benefits of the other solution, then the first solution is dominated. This is in poor words. Now I have to provide a rigorous definition. So let me provide a rigorous definition, and I think it's much better when I use the word S here. I think it's much better if I use X, because X is the decision value. So if you don't mind, please change the symbols. Let's use X. X4, X3, X1, and X2. Sorry for that. Okay, so what does it mean that a solution is dominated by another one? So what does it mean? let me consider the solution xj, and what does it mean that xj is dominated by xi? Two conditions must be met. First, for each k, it should occur that ndk of xj, of xi, is lower or equal than ndk of x. So for each benefit, xi gives greater or equal benefits with respect to xj. Look, I put the greater or equal sign. But of course, if for all the benefits we find a coincidence of the benefit provided by xi with respect to xj, we can't say that the solution is dominated. So here I have to put the greater or equal sign because I can't require that all the benefits are greater. It just suffices that one benefit is greater. So here I have to put a greater or equal sign. But if all the signs are equality, then I can't say that the solution is dominated. So there must exist a k such that ndk of xi is greater than ndk of xj. And here the meaning of the symbol is there must exist one value of k for which we have strict inequality, strict majority of that benefit k for xi with respect to xj. So if you apply this definition, which is easy to understand in practice if you look at the graph, what do you obtain? Let's consider x3. And this is md x3. And this is md1 x3. So if you have x3 here, and you see x4 here, this is dominated by x3. If x5 is here, then x5 is still dominated by x3. Still dominated why? Because you have the same value for mb2, but you have a lower value for mb1. So it's dominated. But if x6 is placed here, we can't say that x6 is dominated by x3. We can't. But be careful, there could exist another solution, x7 here, which dominates x6. So basically what we have to do here, we have to identify the set of the non-dominated solutions. Because those solutions, and only those, deserve our attention. And from a practical point of view, what we do with the BC is extremely easy. If you MD1 x, if you have the same diagram, MD2 x here, what we do with the BC, of course we have the analytical relationship for these two objectives. What we do with the BC is just to make a trial and error procedure. If you make a trial and error procedure, meaning that you take a trial value for x, you can compute MD1 and then MD2. And then you can put a point here. And then you move forward with 1 million of attempts, and then you get you fill in the threshold by 1 million point, and then by applying this definition rigorously, you one by one identify the dominated solutions, and then you are able to depict here the cluster of the points that give the non-dominated solution. This is called the Pareto frontier. Because you see, it's a frontier. It's a frontier or domain. This is something that at the BC we can very easily do once that we define the objective functions. And this is the Pareto frontier. And the Pareto frontier is extremely important because we have to focus our attention on that. And it's also very transparent. And then on the Pareto frontier, then there is a question of saying what is the solution then. Once that we identify the Pareto frontier, which point should I select? And this is the second question. But the first question is to identify in a multi-objective problem what is the Pareto frontier. And then you just have to discriminate between the points of the Pareto frontier. And this is, I think, also exciting. It's a very interesting way of simplifying a problem because you may have 10 objectives. So with 10 objectives, it's impossible to figure out what is the best solution. With the method of the multi-objective optimization and identification of the non-dominated solution, you restrict your attention to a set that is very restricted of solution compared to the starting set. And then you start looking at each one of these, and you will find that some of them are not convenient for some reason, and so you start making your selection. And we will see next time, by introducing the next topic, which is pairwise comparison, how it's possible also to discriminate, to identify, by looking at the Pareto frontier, the best solutions. That's it.